Good afternoon, students. Good afternoon to one and all. Am I audible to all of you? Am I visible and audible to you guys? Yes. So all of you can able to see the screen also, right? Yes. So a very good afternoon once again to all of you. Today we are going to start with the new chapter. Okay. So which is electrochemistry. Got it. So before moving on to the chapter, I would like to ask one question to you all. Okay. So, you all know mobile phones and the laptops which we are using in our daily life. Okay. So, can you tell me how do those cells run? Can anyone give me the reason? Like how do those cells run? How does a mobile run and how does a laptop or a computer, those cells run? Any idea for anyone? How do the cells run? Yeah, very good. Very good. With the help of battery, it is actually electrochemical cell. Everything is running with the help of lithium ion battery, I can say. Okay. And those things can be explained by electrochemistry. Got it? So electrochemistry is having the two terms, which is electro and chemistry. Okay. So means it deals with the interconversions between electrical energy and chemical energy. Got it? Electrochemistry deals with interconversions between electrical energy and chemical energy. Got it? So in today's session, we are going to cover some topics. The first topic is, or the first learning objective for today's session is galvanic cell. The next is electrode potential, then cell potential, and the Nernst equation and the applications of Nernst equation. So these are the target topics which I have taken to cover for today's session. Got it? So let me start with the galvanic cell. Galvanic cell is a type of electrochemical cell. Okay, galvanic cell is a type of electrochemical cell. So I'll come to the types later. First of all, I'll give you the definition for electrochemical cell. Then later on, I will go to the galvanic cell and we will see in detail how the Daniel's galvanic cell works, etc., etc. Got it? Now, what are electrochemical cells? They are the devices which are used to convert electrical energy to chemical energy. Okay, the devices which are used to convert electrical energy to chemical energy is called as electrochemical cell and vice versa. Okay, it can also convert chemical energy to electrical energy. Got it? So both the things are possible and those types of cells are called as electrochemical cell. Now this electrochemical cell is divided into two. There are two types. One is galvanic cell and the other name for galvanic cell is voltaic cell and the other one is electrolytic cell. Got it? So galvanic cell and electrolytic cell are the two types of electrochemical cell. So I'll give you a picture of galvanic cell first. So you can see an example for galvanic cell here in which we have two beakers and some two electrodes are dipped into the two beakers and we have one is anode and the other one is cathode and a salt bridge is connected between those two beakers. Okay, and electrons are moving. So here, chemical energy of a spontaneous redox reaction is converted into electrical energy. So in galvanic cell, what happens? The chemical energy of a spontaneous redox reaction. So what does mean by spontaneous? Spontaneous means continuous. Okay, spontaneous means continuous. So redox reaction. What is meant by redox reaction? The reaction in which the reduction and oxidation taking place simultaneously is called as redox reaction. Okay. So you all might be aware of the term reduction and oxidation in your class 11 itself, no? Can anyone give me the definition for oxidation? So we have 3 to 4 definitions for oxidation as well as for reduction. I would like to get at least one definition for reduction and oxidation from you guys. So Harish is saying it is a gain of oxygen. Okay, oxidation means it is gain of oxygen. Sneha saying loss of electron is called as oxidation. Okay, addition of CO2. Oxygen, loss of hydrogen or removal of hydrogen is reduction. Okay, okay. Very good, students. So, addition of oxygen or removal of hydrogen. Okay. So, this is one definition for oxidation, and the loss of electron is called as oxidation. Very good. And the other way around is the definition for reduction. So, this is called as a redox reaction. And if that redox reaction is spontaneous and the chemical energy of that particular spontaneous redox reaction is getting converted to electrical energy, then we call that as galvanic cell. Okay. Chemical energy turning to electrical energy. Now coming to electrolytic cell, here we have only one beaker. Okay. And 2 electrodes, both anode and cathode, are dipped inside this single beaker, and it is connected to a battery. And we have the electrolytic solution, which is a salt solution basically present inside the beaker, and the cations will move towards cathode and anions will move towards anode. Okay. So this is the setup for electrolytic cell. And here coming to the definition for electrolytic cell, electrical energy is used to carry out a non-spontaneous redox reaction. Okay, so in electrolytic cell, electrical energy is used to carry out a non-spontaneous reaction. Okay, non-spontaneous means discontinuous. Got it? So there spontaneous and here non-spontaneous. And their chemical energy is converted to electrical energy, and here electrical energy is used to carry out the reaction. Okay. So these are the very important basic things you should know about the electrochemical cell. Got it? Any doubt from this? Shall I go for the next slide? Shall I go for the next slide? Yes? Yes. Okay. Good. So now let's discuss in detail about the galvanic cell. Okay. So in the next slide, I'm going to take a galvanic cell. So I have taken a beaker. Okay. And inside the beaker, zinc anode is tipped. And I have a salt solution. It is zinc nitrate salt solution I'm having. Zinc 2 plus and NO3 minus ions are moving inside the solution. And the concentration of the solution is 1 molar. Okay. And here, zinc in the zinc anode, zinc will get oxidized. Zinc will get oxidized. So what is meant by oxidation? It is loss of electrons. So zinc, what it will do, it will lose its 2 electrons and it will be converted to zinc 2 plus. Okay, so zinc in its 0 oxidation state is getting converted to +2 by losing 2 electrons. So it is getting oxidized. And in the other beaker, I am taking a copper nitrate solution where the concentration is 1 molar and copper cathode is dipped inside this. Got it? And here what happens? The copper will get reduced. So I have copper 2 plus ion here in the solution. So those copper 2 plus ion will gain 2 electrons and it will be converted to copper. Okay. So here gain of electron takes place and here in the anode loss of electron takes place. Means at anode oxidation takes place and at cathode reduction takes place. Okay. So you should always keep in your mind that oxidation takes place in anode and reduction takes place in cathode. Okay. And both the electrodes are connected by an external circuit. Okay. With the voltmeter. And the overall cell reaction for this setup is zinc plus copper 2 plus, giving zinc 2 plus and copper. So where zinc is getting oxidized and copper is getting reduced. So it is a redox reaction. So both oxidation and reduction is taking place now. So this reaction is an example for redox reaction. Got it? Salt bridges connecting these two beakers where the electrons are taken away through one beaker and put on, letting down the other beaker. Got it? So any doubt from this? Any doubt from this? So this is the anode and this is the cathode, copper cathode. Okay, so it becomes like this when it undergoes oxidation and reduction. So you can take down, you can keep this LOAN term in your mind. Okay, so left oxidation and in anode, anode will be negative. Anode will be negative and in the left side oxidation occurs. Okay, where in the left side we have zinc, right? Zinc is getting oxidized and it is occurring at anode and the symbol for that anode is negative. Here only in galvanic cell. Only in galvanic cell the symbol for anode is taken as negative. Okay. In all other cases cathode is taken as the negative one, but only in galvanic cell anode is considered as a negative thing. Okay. So this is a short trick kind of thing for you guys to remember the oxidation and where does the oxidation occurs and what is the charge of those electrodes. Okay. So any doubt from the galvanic cell setup for anyone? Can you all able to understand? The points that you have to keep in mind is oxidation occurs at anode and reduction occurs at cathode. Zinc is oxidizing and copper is getting reduced. The overall net reaction you should know. Is it clear for all? Yes. Now let me go for the IUPAC representation of the galvanic cell. So this is the picture of galvanic cell and at anode what we have studied, oxidation half reaction takes place and this is the reaction and IUPAC notation for this is you have to write the metal, solid metal in the left and you have to put a single line, okay, vertical line and to the right side of that line we have to put zinc 2 plus, the oxidized ion, okay, and here the metal is zinc, it is getting oxidized. So this is the oxidation half reaction IUPAC notation. And coming to the reduction half reaction which is occurring at cathode, so what is happening here? Copper 2 plus is gaining 2 electrons and it is getting converted to copper. Okay, so what I have to do? I have to write the copper 2 plus first in IUPAC notation. Then I have to give that vertical line. And after that, to the right of that line, I have to write copper. Okay, now I have to connect these two to write the overall cell reaction. Got it? To write the overall cell reaction, I have to, this is the reaction for which I am going to write the IUPAC representation. So write the oxidation half reaction notation, then reduction half reaction notation with the parallel lines. Okay, vertically parallel lines you have to put to separate those two half reactions. So this is IUPAC notation to represent a redox reaction. Got it? So this is very important again because in the examination they will give you the reaction and they will ask you to write out the find out the IUPAC correct IUPAC representation of a particular cell. Okay, for that you need to check the oxidation state of the element. Okay, here it is 0, here it is +2 and here for zinc it is 2 plus and for copper it is 0. So the zinc is getting oxidized and the copper is getting reduced. So always in the IUPAC notation, I have to write the oxidized half reaction first. Okay, then only I have to write the reduction half reaction by separating them with a double vertical line. So all these things you have to keep in mind and then you have to find out the correct option from the given options. Clear for all of you? Any doubt from this? Shall we go for the next topic? So this is all about the galvanic cell. Okay, the galvanic cell setup and the informations about the galvanic cell and the IUPAC representation of a galvanic cell. Okay, very good. Now let's move on to the next topic, which is electrode potential. So, what is an electrode potential? So, I have the electrolytic solution inside the beaker with an electrode dipped inside it, and there are cations and anions inside the container, right? So, there is some potential difference developed between the electrode and the electrolyte. Okay, so this is called as electrode. Okay, and the solution, it is called as electrolyte. This is called as electrolyte or electrolytic solution. So between these two, there is some potential difference developed. That potential difference which is developed is called as electrode potential. Okay, and this electrode potential is otherwise called as electromotive force of the cell. Electromotive force of the cell. Okay, and in anode, what you see, in anode, what happens? The metal potential will be greater than the solution potential. The metal potential will be greater than the solution potential. Okay, so this is a metal, solid metal, and this is in the aqueous form. Zinc 2+ is in the aqueous form. So if the solution potential is lesser than the metal potential, then oxidation happens for sure in that particular thing, where in which the anode, in which the reaction is taking place in anode. Okay, and in cathode, what happens? The solution potential will be greater than the metal potential. Okay, so if the zinc gains 2 electrons, it becomes zinc in a solid form. Here, what happens? The solution potential will be greater. Means the reduction of ion takes place, and we can write the E reduction for that particular cell. Okay, so we have oxidation, electrode potential, and reduction at electrode potential. Nowadays, according to IUPAC convention, IUPAC you all know, right? International Union of Pure and Applied Chemistry. So according to their convention, standard reduction potentials are called as standard electrode potential. Okay, in some questions, they will give the values in terms of standard electrode potential. Okay, standard electrode potential, and that denotes the standard reduction potential. Electromotive force is nothing but the electrode potential. So each electrode, metal electrodes will have some potential values associated with it. That is called as electrode potential, and we call that as electromotive force of the cell also. Clear? You will study this in detail in your physics, I think so. Is that fine, Harish? So this point is very important. Standard electrode potentials are nowadays called as standard reduction potential, and standard reduction is called as standard electrode potential. Okay. This is the very important point you have to keep in your mind. Now, next I'm going to discuss few things about standard hydrogen electrode, which is called as SHE electrode. Okay, SHE electrode, standard hydrogen electrode. So what is meant by standard condition? Standard means standard temperature and pressure should be there. So what is the standard temperature value and what is the standard pressure value? So standard temperature means 298 Kelvin and standard pressure means 1 bar pressure. I am having a solution, okay, and the concentration is 1 molar. H plus ion is present inside the solution, okay, and it setup is a thing is inserted between this into this system, okay, in which I have one hole for passing this hydrogen gas inside this, and the pressure of the hydrogen gas is 1 bar, okay. And inside this system, I have a rod, right? All of you can able to see the rod, right? So that rod is called as platinum rod, okay. And at the bottom of this rod, you can able to see a metallic block, right? So that is a metallic block. It is a platinum metal actually. So that is the surface of the platinum metallic block in which oxidation and reduction is taking place. Got it? So if a cell is set up with the 298 Kelvin and 1 bar pressure, then we call those electrodes, that platinum electrodes here is called as standard hydrogen electrode. Okay. So first of all, what happens? The hydrogen which is present inside that container, it will lose 2 electrons and it will be converted to H plus ion. Okay, the hydrogen which is going inside this, it will go like this and it will lose electrons. You can able to see the electrons getting lost now. So it will lose the electrons and it will be converted to H plus ions inside the solution. Okay, so there is some electrode potential associated with this and it will be 0 volt. For hydrogen getting oxidized, it is 0 volt. So here the oxidation state of hydrogen is 0 and here it is +1. Means 0 to +1. So oxidation. The oxidation potential is 0. Standard oxidation potential is 0. If I put a naught over here, it denotes the standard value. Got it? Now next what happens? The 2 hydrogen, which is 2H plus, which is coming out by losing its electron, it will again take those 2 electrons and it will be converted to hydrogen again. Okay. So now what is happening? Hydrogen in +1 state, it is getting converted to 0. So +1 to 0. So what it is? It is gaining of electrons. So it is called as reduction. So here the E naught value associated for this reaction is again 0 volt. So for standard hydrogen electrode, both the oxidation reduction potential as well as the reduction potential value will be equal to 0. Okay. So the standard temperature and pressure value you should memorize, and the reactions which is occurring inside the standard hydrogen electrode you should know, and the values of E naught. Okay, which is actually equal to 0. So these are the points you have to keep in mind regarding this electrode. Got it? So any doubt from this? Shall we go for the next? Shall we go for the next? The next topic is electrochemical series. So any doubts so far for anyone, students? Shall we move on to the next slide? So scientists, what they have done, they have used some instruments to find out the value of E naught for many metals. Okay, for many molecules. So, and they have arranged those elements in a series. Okay, and that series is called as electrochemical series. In the series in the sense, they have arranged those elements in the order of increasing or decreasing value of that E naught, and they have proposed a series, and we call that as electrochemical series. And I will give you the tabular column of that. So here is a tabular column. Okay. So in the first column we have the elements, and in the second column we have the reaction, electrode reaction, and in the third column you can find out the E naught values. It is a standard reduction potential values for the corresponding elements. Okay. So in all these cases, gaining of electron takes place. So if an ion is gaining an electron, it is getting converted into a corresponding metal. We are getting the reduced form of the metal ion, and the E naught values are associated with it, and the values are given from more negative to less negative value. Okay. So from lithium till lead, we have the values from more negative to less negative. And after this, we have the value of hydrogen. So this is the value, E naught value for standard hydrogen electrode. So in the last slide only, we have seen that the E naught value is 0. Okay, it is 0 for standard hydrogen electrode. And after this, we have some set of metals. Okay, those metals are copper, mercury, silver, and fluorine. Okay, fluorine is not a metal, and that fluorine element is given here. And here, if you observe the values are given in the positive term. Okay. So if an element or if a metal is having the more positive value, then those elements are called as strong oxidizing element. Okay, it is a strong oxidizing agent. So oxidizing nature increases from less negative, more negative to more positive. Okay, and the reducing character is the opposite of this. So here at the top I have the lithium and it is having the more negative value. So lithium is having the more negative value. So if something is having the more negative E0 value, then it is a reducing agent. And if something is having the more positive value, it is a strong oxidizing agent. So this point is very important. Okay, this point is very important. So you don't have to memorize all these values. The thing is, you just need to keep in mind that if something is having the more negative value, it is a reducing agent, and if it is more positive, it is oxidizing agent. That's all. And for hydrogen, it is 0. Got it? Because in the question, they will give some 4 elements or the 4 reactions which you can see here, and they will give you the E0 values also for those 4. And they will ask you to arrange those 4 elements in the increasing order of oxidizing power or decreasing order of oxidizing power or increasing order of the reduced nature or decreasing order of reduced nature. So in that case, you should not get confused. Okay, more negative, reducing agent, more positive, oxidizing agent. That's all. Okay, so I hope this is clear to all of you. Very easy also. Any doubt from this? Shall I go for the next? Okay. Now let's discuss something related to oxidizing and reducing agent. Okay. So we are going to study how to select an oxidizing agent and how to select a reducing agent. Okay. So I'm going to take 2 reactions for you. So one is with silver plus and the other one is with chromium 3 plus. So both of them are gaining electrons. So silver is gaining 1 electron and it is getting converted to Ag. And chromium 3 plus is gaining 3 electrons and it is getting converted to chromium. Okay. And I'm going to take the electrochemical series also. So what is the E0 value associated with for silver? For silver it is plus 0.80. Right. And for chromium the value is minus 0.74. So if the reduction potential is higher, if the reduction potential is higher, then higher will be the tendency to get reduced and better is the oxidizing agent. So among silver and chromium, silver will undergo reduction and chromium will undergo oxidation. Okay. So if the reduction potential is greater, then it will undergo reduction. Got it? Clear for all of you? So silver is having the greatest E0 value. So it will undergo reduction. The other one will undergo oxidation. Okay. So if the reduction potential is lower, then that will undergo oxidation. So here chromium is having the lowest value of reduction potential. So that will undergo oxidation. Clear? Higher the reduction potential, higher will be the reducing agent. Lower is the reduction potential, higher will be the oxidation character. Got it? Clear? So any doubt, students? Okay. So now let me give you one more relation also. I'll give you one more relation related to reactivity of a metal. I'm going to take the same 2 metals, Ag plus and the Cr3 plus, same values we are taking, and If the reduction potential is lower means if it is more negative, then the reactivity will be more. Okay. So among silver and chromium, chromium is having the more negative value. So means chromium is more reactive metal. Got it? Clear? So if the E0 value is more negative, if it is more negative, then the metal is more reactive in nature. Got it? So the reactivity is more if the E0 value is very less. So they are inversely proportional. They are inversely proportional. E0 value is inversely proportional to the reactivity. If something has to be more reactive, then the E0 value has to be very, very less. Okay? Take down this relation also. So shall I go for one question based on the concept which we have discussed now? Are you all ready to solve that question? Yes or no? Yes. Here in the slide, all of you can able to see the 4 metal couples with their E0 values, right? Arrange these metals in their increasing order of oxidizing power. Which one will come first? Try the answer for this. Cu. Cu is more oxidizing in nature. Aishwarya, you mean that Cu is more oxidizing or it is more reducing? Cu, Fe, Cr is written. Which is more oxidizing? Okay, it is more, copper is more oxidizing, you are trying to say. Okay. Harish is going for Fe. Nagashri is going for Cu. Okay. Cu is having the positive value, right? So it is more oxidizing in nature. Okay. We know that higher the electrode potential, higher will be the oxidizing power. Yeah. So the order will be Cu, Fe, Cr, and at last only zinc. Very good. Very good, students. All of you have selected, got the correct answer for this question. Very good, very good. So this is how you're going to get the questions from this topic. Okay. This is all about the electrode potential, the E0 values. Now let us go for the cell potential. Now let us go for the cell potential. So what is cell potential? What is a cell potential? Again, I'm going to take this galvanic cell in which the oxidation occurs and the E0 value associated with that is 0.76. And at cathode, what happens? Reduction happens and the values associated with it is 0.34 for copper. Overall cell reaction will be zinc plus copper 2 plus giving zinc 2 plus and copper. And I told you how to write the IUPAC notation for this also. Okay. Now, for the cell, I can write the potential value, which is called as E0 of cell. E0 of cell. So it is actually equal to the reduction potential, the reduced couple plus the oxidized couple. Okay, reduced couple plus the oxidized couple. Or I can use one more relation also. E0 of oxidation is equal to minus of E0 of reduction. So this is actually the reduction part and this is the oxidized part. Okay. And if I have to convert both into the reduction potential form, in place of E0 oxidation, put minus E0 of reduction. So here instead of writing this oxidized potential value, I can convert this, okay, into E0 of zinc 2 plus bar zinc. Okay, so it is the reduction potential value. Now I have to change the symbol from plus to minus. So by doing so, I will get one more relation which is equal to E0 of copper 2 plus bar copper minus E naught of zinc 2 plus 2 zinc. Okay. Now both are in terms of reduction potential value. Okay, which is actually equal to E naught of cathode minus E naught of anode for reduction potential. Okay. Because in many questions, they will give you only one type of potential value. Either they will give you the oxidation potential value or the reduction potential value. Mostly you will get the reduction potential value only in the question. Okay, so that's why we are changing the entire thing to the reduction potential value form. Okay, so just remember this relation alone in your mind. So to find out the E naught of any cell, you have to take the reduction potential of cathode minus reduction potential of anode. So is this clear to all of you? So do you have any doubt from this relation which we have discussed now? It should be very, very clear here, because in many numericals, if you see, so all of you might make a mistake over here only. Okay, some students, they will just go in the other way around. It is just with the addition and the subtraction only. But what they will do, they will put the anode potential value here in cathode, and they will make lot of mistakes in that subtraction and addition. And they will end up with the wrong answer. So you guys should not make those kinds of mistakes. Are you all clear with this? Cathode minus anode formula for the reduction to find out the E naught value. Any doubt from this? Shall I go for the next? Yeah. Now, now for the same cell, for the same galvanic cell, okay, this is the reduction potential of zinc, okay, minus 0.76. And for copper, the reduction potential is 0.34. Now, using this formula, cathode minus anode. So, what will be the answer for this question? For this problem, can anyone give me the answer? It is the direct substitution. Take the cathode value and subtract that from the anode. 1.1, sure? Sure? Okay. So it is plus 0.34 minus of minus 0.76. So it will be 1.1 volt. Very good. So for a working of galvanic cell, E naught cell is positive. So if for this galvanic cell, here the E naught cell is coming out to be a positive value. So E naught cell value should be positive for the working of galvanic cell. Clear for all of you? This is how you have to put the values and substitute and get the answer. Now let's go for the feasibility of reaction. Feasibility means the possibility, whether the reaction is possible at this particular condition or not. So that thing we will discuss by using one formula, which is very, very important. Okay. So the formula is the relationship between delta G and E naught. Okay. So delta G is equal to, or delta G naught is equal to minus NF E naught, where delta G naught is the Gibbs free energy of a cell reaction, and N is the number of moles of electrons exchanged, or I can say number of electrons lost or gained. Okay. Number of electrons lost or gained. Okay. This is called as N. And F is the Faraday's constant. F is the Faraday's constant, whose value is 96,000. Approximately, it is 96,500 coulomb per mole. Okay, you should memorize this value. And E naught is the electromotive force, EMF of a cell. Okay, so these are the terms, the terminologies which explains the formula. And here, if the E naught value is greater than 0, then delta G naught will be less than 0. Am I right or wrong? If this E naught value is greater than 0 means, for example, I am taking the value 5. Okay, 5 is greater than 0, right? So minus of N into F into 5. So you can leave this N and F for now. Just take this 5 alone. So if E naught value is 5, then minus of 5 is the answer for delta G naught. Right? So minus 5 is the answer for delta G naught. Means delta G naught is less than 0. Minus 5 is less than 0. Right? Yeah. Delta G naught will be less than 0. If the delta G naught is less than 0 means it is negative. Delta G naught value is negative. So if it is negative, then the reaction is spontaneous. This is very important point. You might have studied this in your class 11 thermodynamics equilibrium lessons. Okay. So for a reaction, if it has to be spontaneous in nature, then the delta G value should be negative. If it is positive, then the reaction is non-spontaneous. Got it? So in the next case, I am going to discuss that only. If the E naught is less than 0, then obviously delta G will be greater than 0. Means delta G value will be positive. Okay, because minus of minus will become plus. So it will be positive. If delta G is equal to positive, then the reaction will be non-spontaneous in nature. Okay. And if E naught cell is equal to 0, if this is going to 0, then minus of 0 is also 0. So delta G is also 0. If it is 0, then we can say that the reaction is in equilibrium with each other. Okay. So can you all able to understand these three cases from the delta G relation? Yes. All of you can able to write down this and understand everything, right? So the relation is important. All the three cases are important, and the terminologies which is representing those formulas again an important thing. So each and everything you should know and understand. Okay. Now based on this, we will solve one question. Calculate the cell potential of the following galvanic cell. So we have 3 cells and 1, 2, 3, 4, 5, 6 cells, 6 couples. E naught value is given to you. Okay. Now you have to find out the cell potential for the given 3 galvanic cells. So how will you find out? So the first is zinc 2 plus versus silver plus silver couple. Okay. So this is the first subdivision for this. So these are the E naught values. And we note that E naught cell is equal to cathode minus anode. So for the first given cell, so what will come in cathode, silver or zinc? Who will come in the cathode part? Who is getting reduced? Cathode means in which the reduction occurs. Anode means in which the oxidation occurs. So from the IUPAC notation, IUPAC representation of a cell, yeah, very good. Silver is getting reduced from +1 to 0. And its value is, what is the reduction potential value for silver? It is 0.80 minus of, what is for anode? So here zinc is getting oxidized. So where is the zinc value? Yeah, here we have, but yeah, here we have the zinc value, just minus of minus 0.76 you have to put. And the answer will be, yeah, 1.56. Answer is 1.56. Nagashri, how did you arrive at this answer, minus 0.70? You have made some mistakes, I think so. Actually, we have to substitute the reduction potential value for this anode, one which is happening at anode, right? Here, the reduction potential value is alone given here. So just take that and substitute it directly. Okay, you don't have to look into the cell notation. So from the cell notation, we are finding out which is getting oxidized and which is getting reduced. That's all. Got it? Okay, fine. Now coming to the next subdivision. Iron is getting oxidized and copper is getting reduced. So what we have to do? Reduction occurs at cathode, no? So copper is getting reduced here, and the copper couple E naught value is given to us in the question, okay, which is 0.34 minus. And what about for the anode? Anode is Fe2 plus Fe. Yeah, Fe2 plus Fe, and its value is also given here. Reduced potential value is also given here, minus of minus 0.44, and that will give 0.78. Very good. 0.78. Good. Now coming to the third reaction. So gold is getting oxidized and chromium is getting reduced. So what will be the value for reduction? Reduction is chromium. Reduced ion is chromium. Okay. And it is 0.74 minus of 1.22. Got it? So we'll get minus 2.16. Okay. It is actually minus. It is not plus. It is a typing mistake. Okay. Minus 0.74 minus of plus 1.42. So did you all get this answer for the third reaction? Any doubt? Yes? Okay. Good. So this is how we have to find out the E naught cell value by using this formula. Okay. So in one place you all will make mistake, that is here. Okay. So here you might have seen that zinc is going to zinc 2 plus, but here we have zinc 2 plus 2 zinc. So let me change the sign from negative to positive here, and let me change here, and I will get the answer which is actually wrong. So this kind of mistake we should not make. Okay. Okay. So Sneha want me to explain the third thing. So this is a typing mistake, and we'll have negative here. So chromium is getting reduced, okay, in which it is putting at anode, cathode. So in cathode, reduction happens because chromium is getting reduced. So chromium value is, reduction potential value is minus 0.74, and minus of the oxidized ion is gold, and its reduction potential value is plus 1.42. So I'm just substituting and getting the answer. Clear, Sneha? Any doubt? It's also direct substitution only. Nothing to worry here. The answer is given in E naught value is given in terms of positive for that item. For copper and gold, the value is in positive. That's all. Okay. This is about the E naught value. So far we have discussed the galvanic cell, electrode potential, and cell potential. Okay. The next topic is Nernst equation, which is very, very important. Nernst equation is very, very important. It was proposed by the scientist Nernst, and we have kept his name for that equation. Okay. Very important for solving the problems for NEET and JEE. Got it? So here I am going to take a general reaction in which M and N are the metal and metal ions. So for this is a general reaction. So here M is getting reduced and N is getting oxidized. Okay, N can be zinc and M can be copper. Okay, we can take any example also. And in thermodynamics lesson of class 11, we might have studied one relation between delta G and Q. Can you give me the relation? Many of you remember that relation which relates delta G and Q? Any idea? Yeah, it is delta G equal to delta G naught plus RT ln Q. Okay, this is the relation. Delta G is equal to minus NF E, and delta G naught is equal to minus NF E naught. Okay, delta G is equal to minus NF E, and delta G naught is equal to minus NF E naught. So what is the difference between delta G and delta G naught? If I am putting not over here, it denotes the standard condition. That's all. Okay. So what I can do, I can substitute these two values here in this delta G place and delta G naught place. By substituting, I will get a relation like this. And here I can divide the entire equation by NF. If I am dividing, this NF will go away, and here also it will get cancel out each other, and here I will get NF in the denominator. Okay, I will get a relation like this. So which is a relationship between E cell and E naught cell with Q. Okay, so this is one equation for Nernst. Now, bringing this equation to the next slide, by having the same reaction, this Q is nothing but the reaction quotient, where it is equal to the oxidized ion concentration divided by the reduced ion concentration. So N is getting oxidized. So this is the oxidized ion that I have to put in the numerator. Then the reduced ion is M that I have to put in the denominator. So in place of Q in the previous equation which I have given, substitute N plus by Mn plus in that place of Q. So if you substitute, you will get one relation like this, where F is the Faraday's constant. F is the Faraday's constant here. Value is 96,500, and the logarithmic function of A is 2.303 into log A. So if I want to convert this Ln to log, I have to multiply by 2.303 number. Okay. And I'm going to take the temperature value as 298 Kelvin. Temperature value as 298 Kelvin. By taking the temperature as 298 Kelvin and multiplying with the R value and dividing with the F value, I will get one final number which is equal to 0.059. Okay. If I multiply and divide this entire thing, which is a constant value, I will get one number which is, yeah, very good, Bhagat. It is 0.059. Okay, divided by N. So you know what is E cell, you know what is E naught cell, and you know what is N also, right? N is the number of electrons lost or gained into logarithmic function of oxidized ion concentration divided by reduced ion concentration. This is the Nernst equation. This is the Nernst equation. So in place of N and L, you can substitute Q also. If Q is given to you in the question, then you can directly substitute. Okay. Or if only oxidized reduced concentration is given to us, then we can substitute those values in the equation and get the answer. Is that clear for all of you? So mostly in the competitive examinations in JEE and NEET, you will be using this formula only. Got it? So in many of the previous year questions from this lesson, at least one question from Nernst equation is being asked. Is that clear for all of you? You don't have to memorize anything. Only thing is you have to memorize this last equation. That's all. Rest other things are just the derivation of this. You're not going to use those things in any of your formula. Okay. You're not going to multiply R and T, or you are not going to divide F. Nothing. They have multiplied and divided everything, and they have got one value which is 0.05. So that thing you have to keep it. Okay. Okay, students. So this is enough for today, and tomorrow we will continue with the problems from Nernst equation, and then we will carry on with the other topics. Got it? So today we have studied galvanic cell, cell potential, electrode potential, and some parts of Nernst equation, the theory part of Nernst equation. Okay. Yeah. How to find out the log? Log value will be given to you in the question for NEET and JEE. Okay, you don't have to. For some log 2, log 3, log 4 and all, you have to keep in mind that I will give you the values to keep in mind in the next class. For the big numbers and all, they will give you in the question itself. Okay. Is it clear? Yeah. Okay. Thank you so much, students, for listening to today's lecture. Meet you all in the next.